In this segment, we are going to look at approximate median. Just to remind ourselves, we have introduced the notion of streaming. We have also looked at approximate counting that requires just O of log n bits. And we have looked at sampling k items out of the n item stream when we don't know n, both with and without replacement. This is called reservoir sampling. We are now ready to apply our ideas to finding an approximate median. And just to recall, we've already looked at the problem of finding the exact median. It requires multiple passes. We looked at it from the classical RAM model perspective, and if you recall, we had to sample some n to the 3/4 number of items. We had to find the median, and then we had to step back from the median, basically find 2 items within the samples, then go through the passes again, find items that fell within the 2 items in the sample, so on and so forth. So that requires a little bit more work, requires multiple passes, requires n to the 3/4 memory, and so on and so forth. It still works as a streaming algorithm, but you will need multiple passes and you will need n to the 3/4 memory. So what we are going to look at today is requires a lot less memory and just a single pass. In particular, this approximate median algorithm will only require O of epsilon to the -2 times log 1 over delta amount of memory, and it will require exactly 1 pass. The algorithm itself is very simple. All we have to do is sample some t items with replacement from the stream, and we know how to do that. And we need to simply return the median of those t samples. So it is probably the most natural algorithm that you can think of. Of course, the only thing that remains is for us to know what the value of t is, and that's going to be our primary concern. So if we plug in the appropriate value of t, we will get an approximate median. But for that, we first need to be very clear about what we mean by an approximate median. We all know what the true median of a set of n items is. You take the sorted view, and the true median is right in the middle. It is simply the item with rank n over 2, and by rank here we mean the position in the sorted view. So now the question is, what is an approximate median? And notice that we are requiring an epsilon approximate median. So there's a parameter. So what is an epsilon approximate median? Well, consider this range where this item is of rank n over 2 minus epsilon n, and the item to the right is of rank n over 2 plus epsilon n. Now, any item within this range of rank n over 2 minus epsilon n up to rank n over 2 plus epsilon n is an epsilon approximate median. Now that we know what an epsilon approximate median is, now let us set about finding the appropriate t value for which our algorithm will output an epsilon approximate median with probability at least 1 minus delta. So our goal is to output an epsilon approximate median with probability at least 1 minus delta. So how will this not happen? So that's the important question. So let's again look at the sorted view. In this sorted view, we certainly don't want to output an item that is shaded red, because that's falling outside of the acceptable range for an epsilon approximate median. In particular, when we look at the sorted view of the t samples, there are two bad events that we want to avoid. We want to avoid getting more than t by 2 items, or t by 2 or more items from the red range in the left, and similarly we also want to avoid getting more than t by 2 items uh, from the red range in the right. These are the two bad events and we want to avoid them. So the question now is, what is an appropriate value of t such that these two bad events can be avoided? So for that, let us define a random variable. Yi is our random variable, and it's equal to 1 if the ith item in the sample. Now you just think of the sample as being ordered in some way, not necessarily sorted, and the yi equal to 1 if the ith item in the sample has rank less than n by 2 minus epsilon n. Basically, this captures the event that the ith item is coming from the red range on the left. Okay, so such items, we don't want too many such items. So with that being the case, let's define y to be the summation overall overall I ranging from 1 to t yi. And of course, we know that expectation of yi equals to half minus epsilon t. Our bad event, the event that t by 2 or more items are coming in the sample are coming from this red range in the left, can be captured in the following way. That's simply the event y is greater than or equal to t by 2. And of course, we want the probability of this event to be small. In particular, we want this probability to be no more than delta by 2. Why delta by 2? Because there is a mirror image, a symmetric other bad event that we also want to avoid with probability delta by 2. So the two bad events put together using the union bound, we can say that the bad events don't occur with probability or occur with probability at most delta, and therefore the final outcome is correct with probability at least 1 minus delta. So that's the goal. And now notice that these yi's are independent. So applying Chernoff bounds, we look at the probability y greater than or equal to t by 2, and we rewrite it as probability y greater than or equal to half minus epsilon times t, and that's mu, times 1 plus epsilon. This is smaller than e to the minus half minus epsilon times t epsilon squared divided by 3, and we want this whole probability to be less than or equal to delta by 2. So if you work out the mathematics, we can conclude that this inequality can be achieved with t belonging to O of epsilon to the minus 2 times log 1 by delta. In fact, I would encourage you to find out the exact t value for which this inequality holds. So with that, we conclude our lecture on introducing streaming, looking at the problem of counting the number of items in a stream in a single pass using very small memory, the problem of sampling items, some k items from a stream, both with and without replacement. And finally, now we have looked at the problem of finding the median, an approximate median from the stream using a very small amount of memory, in particular O of epsilon to the minus 2 times log 1 over delta memory to and a single pass to find an epsilon approximate median in our stream.